There is an engine so quiet, so efficient, and so ruthlessly reliable that NASA ran one for over 12 years straight without a single repair, and almost nobody in the West is building it at scale. That engine is not a fusion reactor. It is not some exotic superconductor that requires laboratories kept colder than outer space. It was invented in 1816 by a Scottish minister trying to stop his parishioners from being killed by exploding steam boilers. It converts heat into motion with an efficiency that shames the internal combustion engines powering almost every vehicle on Earth. And right now, beneath the surface of the Pacific Ocean, a fleet of submarines runs on it in near-perfect silence, and the United States Navy struggles to hear them coming. This is the story of the Stirling engine, how the West discovered it, proved it, funded it, and then quietly buried it to protect a business model, and how China picked it up, industrialized it, and turned it into one of the most strategically significant propulsion technologies in the world today. Let's go back to the beginning. The year is 1816. A young reverend named Robert Stirling stands in a Scottish parish watching workers die, not in war, not in floods. In factories and mines, workers were being scalded and shredded because the steam boilers of the early Industrial Revolution had a habit of exploding without warning. The metallurgy of the time could not keep up with the pressure demands of steam engines. Seals failed. Rivets gave way. Men died. Stirling's invention was a direct answer to that danger. His engine used no boiler and produced no explosive pressure. Instead of superheating water until it became a dangerous high-pressure steam, his design moved a fixed quantity of gas, typically air, back and forth between a hot end and a cold end inside a sealed cylinder. The gas expanded when hot and contracted when cold, and that rhythmic expansion and contraction pushed pistons and produced mechanical work. No combustion inside the cylinder, no steam, no explosive risk. The heat source, whatever it was, applied from the outside. The elegance of the design is almost offensive in its simplicity. The Stirling engine can run on any heat source whatsoever. Burning wood, burning gas, nuclear decay, concentrated sunlight, waste heat from an industrial process. If one end is hot and the other is cold, the engine runs. And because the gas inside never escapes and never burns, there are no exhaust valves, no spark plugs, no fuel injectors, none of the hundreds of components that wear out in a conventional internal combustion engine. The moving parts are minimal. The mechanical noise is almost non-existent. For a few decades in the 19th century, Stirling engines were genuinely competitive. They powered pumps and fans in factories across Britain. They ran quietly where steam engines thundered dangerously. Then, something happened that would define the engine's fate for the next 200 years. Stirling engines enjoyed some small degree of success for about a century, until early in the 20th century, when competition from electric motors and relatively lightweight internal combustion engines relegated the rather unwieldy Stirling engine into relative obscurity and what appeared would become irretrievable obsolescence. The internal combustion engine was faster to power up, cheaper to manufacture at scale, and fit neatly into the car revolution that was about to reshape the world. The Stirling engine, with its slow thermal response and bulkier frame, simply could not compete in that context. It faded from industrial memory. By the 1930s, most engineering schools had stopped teaching it. The patents had expired, the knowledge scattered. Then a Dutch electronics company decided to rescue it. Philips began research on Stirling engines around 1938, initially aimed at developing small thermal power electric generators for radios and similar equipment, for use in remote areas where storage batteries were not available, but kerosene or other liquid fuel might be had. The idea was elegant. Instead of shipping heavy batteries to villages in Africa or Southeast Asia, you could ship a small Stirling generator that ran on whatever fuel was locally available, kerosene, charcoal, dried dung, and it would power a radio receiver. The revitalization of the Stirling engine occurred at Philips Research Laboratories in Eindhoven, where dozens of Stirling engines were designed, manufactured, and tested over a period of almost 40 years. The work that came out of Eindhoven was remarkable. Philips engineers solved fundamental problems of sealing, heat transfer, and material fatigue that had plagued the engine for a century. They pushed efficiencies far beyond what anyone had achieved before. They demonstrated that a well-engineered Stirling engine could run for years on end, with almost no maintenance. But then the market shifted under them. Improvements in radio valves, batteries, and the invention of the transistor later removed the need for these small generating sets. The original reason Philips had started the whole program simply evaporated. The company had spent decades and built extraordinary engineering knowledge, but the application they had designed for no longer existed. They pivoted. In about 1958, Philips aroused the automobile manufacturing community by revealing an operating, single-cylinder Stirling engine that exhibited a thermal efficiency about half, again better than that of contemporary internal combustion engines. Think about what that means. Half again better. If a gasoline engine of the time converted roughly 25% of its fuel energy into motion, a comparable Stirling was approaching 38 to 40%. The rest of the fuel, in a conventional engine, simply vanished as heat out of the exhaust. The Stirling wasted almost none of it. The auto industry was briefly, genuinely interested. Then it was not. That excitement dwindled because the priorities in automotive applications are high performance and high efficiency, and Stirling engines with these characteristics are fraught with design problems. A gasoline engine responds instantly when you press the accelerator. The Stirling engine, because it heats slowly from the outside, has a thermal lag. You press the pedal, and the engine takes a moment to respond. For a commuter car on a highway, that is disqualifying. It does not matter that the engine is more efficient at steady cruise. Drivers want immediate response. NASA picked up the thread in the late 1970s. NASA developed modified Stirling engine-based automobiles in the late 1970s as part of their automotive Stirling engine program, with test projects named Mod I and Mod II, developed by Philips and American Motors Corporation. Mod II delivered exceptional results in the form of a super-efficient automobile engine that achieved a thermal efficiency of 38.5%. But soon the funding was cut down. Automakers lost interest in the program, and the projects could never reach the stage of commercial production. Let me be direct about what happened here, because it matters enormously to the rest of this story. The Stirling engine was not abandoned because it failed. It was abandoned because it succeeded in the wrong context. Every time it was tested seriously, it performed. Every time it approached the market was structured in a way that made its particular strengths irrelevant. A conventional power grid is built around turbines that run at constant load and respond to demand by spinning faster or slower. An internal combustion engine is built around the assumption that instant throttle response is non-negotiable. An electric utility makes money selling kilowatt hours, and a more efficient generator that requires less fuel is not a business advantage unless fuel costs are the dominant expense and the utility owns the fuel supply. In each case, the Stirling engine arrived with a proposition the existing infrastructure had no room for. This is not a conspiracy. It is something quieter and more powerful than a conspiracy. It is institutional inertia and the logic of sunk capital. The fossil fuel electricity model works. It is paid for. The auto industry had spent half a century building supply chains, dealerships, mechanics, and consumer expectations around internal combustion engines. No single company was going to absorb the cost of retooling around a different engine technology when the existing one was, by most metrics, adequate. So the knowledge went into journals, patents, and university laboratories. Companies that tried to commercialize Stirling engines in the 1980s and 1990s found the funding environment hostile and the market indifferent. Several shut down. The Western world moved on to turbochargers and fuel injection to squeeze more efficiency from internal combustion engines, accepted a theoretical ceiling, and called it progress. Meanwhile, NASA kept running its engines, Here is where the story pivots towards something extraordinary. While the commercial Stirling engine was dying in the marketplace, the engineering case for it was getting stronger with every decade of testing. The problem had never been the physics. The physics were always beautiful. The problem was the application. What application requires an engine that is extremely quiet, extremely efficient, uses no internal combustion, can run on any external heat source, has almost no moving parts to wear out, and can operate for years without maintenance? If you are thinking of a submarine, you are thinking correctly. Swedish Gotland-class submarines feature Stirling engine air-independent propulsion systems, enabling them to avoid going to the surface to charge the batteries, thus increasing the submerged endurance from days to weeks. The Stirling engine is quiet and vibration-free, so no vibrations spread out to the hull, making the submarine silent in the water and therefore difficult to find. A conventional diesel-electric submarine has a fundamental vulnerability. It carries batteries for silent underwater running, but those batteries run out. When they do, the submarine must rise close enough to the surface to run a snorkel, which draws air in for the diesel engines to recharge the batteries. That snorkel exposure is detectable. Radar can spot it. Aircraft can hunt it. The moment a diesel submarine snorkels, it announces its presence. Air-independent propulsion eliminates that vulnerability. The Stirling engine, running on stored liquid oxygen instead of atmospheric air, can keep the submarine's batteries charged for weeks without ever surfacing. The submarine becomes, for practical, tactical purposes, as hard to find as a nuclear boat, not quite as fast, not as long-ranged, but nearly as invisible, at a fraction of the cost. The Swedish company Kockums developed this application in the 1980s and 1990s, and it worked brilliantly. Sweden's Gotland-class submarines are equipped with 2 Kockums Stirling air-independent propulsion units, each providing up to 75 kilowatts, giving the submarine the capacity for 2 weeks of air-independent propulsion at a speed of 5 knots without snorting. 75 kilowatts per unit, 2 units. That was the state-of-the-art in the West. Japan licensed the technology and put it in their Soryu-class submarines, each unit producing less than 80 kilowatts. The United States, which operates an all-nuclear submarine fleet, had no direct use for the technology and no institutional incentive to push its development further. It remained a niche solution for smaller navies that could not afford nuclear boats. Here is where NASA's record becomes relevant again, and where the story of the Stirling engine takes a turn that deserves to be better known in the West. At NASA's Glenn Research Center, engineers set a record of operating a free-piston Stirling engine at full power for over 110,000 hours of cumulative operation, and it was still running without issue. 110,000 hours. That is more than 12 continuous years at full power. Think about that for a moment. The average car engine, driven normally, might accumulate 3,000 hours of operation over its entire lifespan. NASA's Stirling engine ran for the equivalent of roughly 37 car lifetimes without a single repair. Free-floating pistons inside the engine move continuously at high frequency, but there is no contact with other parts. Engineers have virtually eliminated the mechanisms of wear and tear. The evaluation found no performance degradation, indicating that these units demonstrated the reliability necessary for a long-life dynamic power converter. No wear, no degradation. After 12 years. In what other engine technology on Earth can you say that? The efficiency figures are equally striking. NASA's free-piston Stirling engines were designed to convert the heat from decaying radioactive plutonium into electricity for deep space probes. Stirling power converters in radioisotope power systems can potentially reduce the amount of plutonium fuel required to achieve a given power level by a factor of 4, all while maintaining the long life and high reliability needed to support space missions. 4 times less fuel for the same power output. That is not a marginal improvement. That is a transformation. The best thermoelectric converters used in current deep space probes achieve efficiencies around 6 to 8%. Stirling converters operating at similar temperature ranges achieve efficiency figures approaching 90% of theoretical maximum, with real-world demonstrations consistently above 35%. In terms of converting a heat source into usable power, nothing else comes close, and the United States is using this technology to power probes to Neptune. It is not using it to power cities, factories, or strategically critical military hardware, China noticed. I want to be precise about the timeline here, because the precision matters. China did not stumble onto the Stirling engine as some kind of accidental discovery. Chinese engineers studied the Western literature systematically. They understood exactly what the technology was capable of and exactly why the West had failed to scale it, and they made a strategic decision to do what the West would not. When China was developing the Type 39B submarine, it realized the localized modification of the air-independent propulsion power system, which is much more advanced than the Japanese Kanglong class. Based on imported Swedish air-independent propulsion technology, China made an upgrade with a new Stirling engine. That is the core of the story. China did not invent the Stirling engine. China took Western Stirling technology, licensed it legally, studied it, and then methodically surpassed the people who invented it. The country's first large-bore Stirling engine basic prototype successfully completed performance tests at the 711th Research Institute of China State Shipbuilding Corporation. This prototype has a rated power of 320 kilowatts and a thermal power conversion efficiency of 40%, which is the highest level known in the world for a Stirling engine. 320 kilowatts. 40% thermal efficiency. Let that sink in, alongside the comparison that puts it in context. China's new 320 kilowatt Stirling engine, if equipped to its air-independent propulsion submarines, will reach 4 times the power of Japan's Soryu-class air-independent propulsion submarines, which are equipped with a Stirling engine of less than 80 kilowatts, 4 times the power of Japan's best. Japan, the country that had operated Stirling submarine engines for decades and was considered the most advanced user of the technology in Asia. China did not just catch up. China built something in a different category. The engine can spawn a series of variations to suit the need of power supply, ranging from 100 kilowatts to several megawatts, and is very suitable to be developed into a portable microreactor power generator used in special environments such as polar regions, remote islands, and Gobi Desert regions. This is no longer just a submarine engine. This is a platform technology, an engine family that scales from 100 kilowatts to the megawatt range, that runs on any heat source including nuclear, that produces almost no acoustic signature, that can operate for years without maintenance. The military applications are obvious. The civilian applications, in energy-scarce or grid-remote environments, are equally vast. Now look at the fleet those engines are going into. China does not have to worry about producing a massive fleet of expensive and difficult-to-produce nuclear-powered submarines. It has 2 types of diesel-electric submarines that use the eerily quiet Stirling air-independent propulsion. The best of these models are the Type 39A and Type 39C Yuan class boats. The Type 39A and C Yuan class forms the operational core of China's conventional submarine fleet, with approximately 21 air-independent propulsion-equipped boats currently in service within a total diesel-electric inventory of 48 attack submarines, according to global defense assessments. They are easier and cheaper to produce, and China has the shipyards to build them quickly. The Chinese are making Yuan-class boats at a remarkable pace. They can produce more than one at the same time, while the United States and its allies struggle to keep up. The Type 39A is an ultra-quiet attack boat equipped with air-independent propulsion. This key technology allows it to remain submerged for weeks, making it exceptionally stealthy and even quieter than some nuclear submarines. Here is the geopolitical weight of that sentence. Even quieter than some nuclear submarines. A diesel-electric boat that costs a fraction of a nuclear submarine, built at a pace the United States cannot match, running on an engine the West invented and then left behind, operating silently for weeks, in contested waters where the 7th Fleet operates every day. The United States Navy runs a purely nuclear submarine force. It has no air-independent propulsion program. It made a deliberate strategic choice decades ago to invest entirely in nuclear propulsion, which has real advantages in deep ocean, long-range operations. But that choice also means there is no American institutional expertise in Stirling submarine propulsion, no American shipyard producing these boats, no American engineering pipeline developing the next generation of this technology. The success of the prototype is a milestone and a major breakthrough China has made in key technologies and craftsmanship in developing such engines, and laid down the foundations for its development of megawatt-class Stirling engines. Megawatt class. The trajectory is clear. A 320 kilowatt engine was the record in 2021. The engineering path to 10 times that power is already being mapped out. Honestly, when I look at this history in full, what strikes me most is not that China did something aggressive or unusual. What strikes me is how predictable the Western failure was. Every institution that encountered the Stirling engine in the 20th century made a locally rational decision to set it aside. The auto industry needed instant throttle response. The power grid needed grid-compatible generators. The military wanted nuclear range. Each individual decision was defensible. The cumulative result was the abandonment of one of the most capable engine concepts ever demonstrated. China looked at the same technology and asked a different question. Not can this replace what we already have, but what can this do that nothing else can do? The answer was, it can hide a submarine from the most sophisticated naval force in history. By 2035, China's submarine fleet is projected to reach approximately 80 units, comprising both diesel-electric and nuclear-powered types, with efforts focused on replacing older platforms and increasing capability, 80 submarines. The Stirling engine powering the conventional portion of that fleet. Built at scale, with the full manufacturing weight of China State Shipbuilding Corporation behind it, improved to world record power and efficiency, and now being scaled toward megawatt-class variants. What was a museum curiosity in the West is a production line reality in China. What American engineers demonstrated running for 12 years without a repair in a NASA laboratory is now running silently under the South China Sea. The Stirling engine did not fail. The institutions that were supposed to build it failed. And the cost of that institutional failure is not being paid in engineering journals. It is being paid in the balance of power in the Pacific. If you want to follow stories like this one, where the technology that shapes the world is hiding in plain sight, subscribe to the channel. The history is always longer than the headlines. And here is the question I want to leave you with. Is the Stirling engine a cautionary tale about the West's inability to build what it invents? Or is China's success with it simply proof that strategic patience in technology always beats short-term market logic? What do you think?